of a quadrupole anisotropy, and the rate of rotation is given by this little formula here. And so what you could do is look for a quadrupole anisotropy with rotational symmetry and say, wow, just as the dipole is due to our linear motion, this quadrupole is due to our angular motion. And so what this would mean, if this was true, is that the cosmic background radiation determines an absolute standard of rest, not just a standard of velocity at rest, but also a rotational rest velocity. The dipole giving you the translation and the quadrupole the rotation. And I got quite excited about this. I was about to write this up. And my colleague Tony Lazenby and his colleagues at Cambridge said this is wrong. What you can do is a local calculation of how antennas work, and you can show a local rotation of the antenna does not cause an anisotropy in the cosmic background. So this is a rather interesting case in which I was misled by these Machian ideas. So it's quite fun, though, because if you look at that, it's kind of plausible in the line of the preceding discussion. But what it does say is that we can assign a quadrupole anisotropy to the microwave background if it was rotating, and you can use this to limit the amount of rotation of the surface of last scattering relative to us, which most people would assume is zero, but anyhow, this is saying it has actually observable effects. Okay, now, the last and in a sense the most important thing I want to talk about is the arrow of time. Aha! And the point here is that fundamental physics is reversible, time reversible, except for a very weak effect in the weak interactions. And so the major question, which many physicists have thought about down the past decades, is where does the macroscopic arrow of time come from, given that the microscopic physics is time reversible? And why is the arrow of time the same everywhere? Given that microscopic physics is time reversible, could it happen that over there time is running backwards to over here? Could the breaking of symmetry involved in choosing the arrow of time come out differently in different parts of the universe? Now, it's interesting to start off with a simple mechanical effect, a clock escapement, which can only rotate that way, as you can see, because you've got a spring pressing this thing against that wheel, and it can only go one way. When you have a clock escapement and a ratchet, it only goes one way in progress. The simple question is, how does this incredibly simple mechanical device know which is the future direction of time and which is the past? If you run a film of its action, you can correctly order the film in time. You can see the way the thing is going. But if you reverse time, you'll get spirals going the other way. And if you reverse the arrow of time, this way is the way it spirals in space the one way. If you reverse the arrow of time, it would go the other way. And the question is, how does this simple mechanism know which way to rotate in space-time? The local space-time does not determine the direction of time. It's the flat space-time which you've been talking about over here. There is no arrow of time in that local space-time structure. And the more you think about that, the more puzzling this is. In electromagnetic theory, you have time going up space sideways, and you send off a signal there, and it's received there. But Maxwell's equations are time symmetric. You can write them out in terms of a Kirchhoff integral with a plus or with a minus. And you get the retarded solution as well as the advanced. And according to Maxwell's equations by themselves, it is perfectly possible you will receive the signal before it was sent or after it was sent. Why do we only see the retarded solutions? A famous question. This has involved many people, including Wheeler and Feynman. And in a sense, this is what led Feynman to his whole views on particles and antiparticles, was thinking about this. The advanced solution, in which we see the image before the light is emitted, is excluded by hand. We get both solutions from our equations, and we arbitrarily chop the one and not the other one when we do the mathematics. It is not excluded by the local fundamental physics because the Maxwell's equations are time symmetric. Now, what this has to be due to, according to most people, is a difference in boundary conditions at the very start of the universe and at the very end. And as I say, they're famous papers by Wheeler and Feynman. There's a beautiful discussion of this in Roger Penrose's book, The Emperor's New Mind, and I really recommend Roger Penrose's book for a discussion of the arrow of time. So the idea here is the local of arrow of time, the direction of increase of entropy, is determined by the very distant universe in both space and time. There is a difference in the boundary conditions on the past and the future light cones, and that's what gives the local arrow of time. Now, that's incredibly important. That's a hugely fundamental effect for local physics, the fact that physics is not time symmetric.
Again, is that put in by hand?
The difference in boundary conditions. Yeah, you assume, well, for instance, Wheeler and Feynman had their absorbers in the future and not in the past, for instance.
But that begs the question. You put it in by hand.
Well,
so
yeah,
what's the arrow time? I decided that.
It's what you're reducing it is you're saying that the local solution is determined by the equations and the boundary conditions. The arrow of time isn't in the equation, so it's got to be in the boundary conditions. There's an arrow of time in quantum theory. There's a choice of advanced and retarded Green's functions. When we had the Green's functions calculation earlier, he didn't tell you he was only choosing the one and not the other one. Buried in the I epsilon, exactly. There was an equal and opposite solution with a minus I epsilon in which things go backwards in time instead of forward. And the local physics does not tell you which is the way things should happen. If you know about the measurement problem, the collapse of the wave function, when a measurement takes place, the wave function is not an eigenfunction, and then a measurement takes place, and immediately afterward it is an eigenfunction. That's a dramatic difference from non-eigenfunction to eigenfunction. It's got an arrow of time in it. How does the quantum state know in which way it should collapse in time, backwards or forwards? It's not governed by the Schrödinger equation. And so this may be, in some sense, how does this know where the arrow of time comes from? Well, Roger Penrose suggests it's linked through to quantum gravity, which is something I find difficult to believe, but at least it's an attempt on an explanation. Most people don't try to explain it. Now, some people don't believe in collapse of the wave function. Instead, they believe in the many worlds view, where there's a splitting of the universe into multiple branches. That's an attempt to get around the measurement problem in quantum mechanics. This is time asymmetric too. How does the universe know in which direction to do its splitting into multiple branches? It's just equally, you don't solve the arrow of time problem by going to multiple universes.
Can I ask a question about the collapse of wave function?
Yeah.
Do you believe that measurement necessarily has to do with consciousness?
Do I believe? No, I don't believe that, but John Wheeler does.
But what does it mean to have something which is not conscious doing a measurement?
Can I say that this is going to take us too far away? Let's have a nice discussion about this later on. Now, one of the most interesting is entropy in thermodynamics. When you relate microstates to macrostates by coarse graining, and the essential feature of entropy is coarse graining, where you shove a whole lot of microstates in and label them by one macrostate. And you get bottom-up interaction by which microevents determine macroevents. The most probable macrostates have the highest entropy because there's a huge amount of hidden information. The most probable macrostates are more probable because if you just scatter states randomly, they are most probable, so they're most likely to turn up because they have the largest number of microstates. Now, Boltzmann produced this beautiful H theorem in which he proved that evolution in certain circumstances to a higher entropy state is going to take place. It's more probable, or as people say, more disordered. That's a very misleading way of talking. And there's a beautiful proof of Boltzmann H theorem in general relativity theory by Jürgen Ellis. You can do this exactly in general relativity for kinetic theory, and you can prove the H theorem, Boltzmann H theorem. Entropy increases to the future. Success, big tick, until you realize the proof works whichever way you choose the arrow of time. Disaster. And this is something that Roger Penrose talks about as well in his very beautiful writing on this. This works for both directions of time. It does not choose which is the direction of time. So the attempt to determine the arrow of time from microphysics to macrophysics through Boltzmann's H theorem fails. And actually, if you think about it, it's got to fail. Because in the microphysics, there isn't any choice of the arrow of time. There is no way that the macrophysics can choose a direction because it isn't there in the microphysics. So somehow or other, it has to come from initial conditions as it can't come from the equations. And I want then to talk about gravity and structure formation. It's the same story. We're always told gravity causes structure to form, but if you think about it, that is true both whichever way you choose the arrow of time. because the Newtonian equations are also time symmetric. Now, it's modified by the expanding universe, and that's what gives the direction. And also gives, that's what gives the arrow of time. But the point about this is nobody has got a proper link of gravity to entropy. You all know the standard picture about how you have this box and you open that and it spreads out uniformly. That's true when there's no gravity. When you turn gravity on, that is not what happens. And so all of the stuff about, in fact, gravity leads to spontaneous structure formation of galaxies, stars, and planets. Now, the time reverse can take place because there's no arrow of time. Well, the arrow of time in this comes when you open the door, but then it's still, how does it know which is the future and which is the past in order to go through?
In the second picture, why do you have to open the door?
You don't have to open the door. It's just to link it. It's just to say that what people normally say is not what happens when gravity's turned on. Every single first-grade textbook on physics does not point this out. What gives the arrow of time? And the answer seems to be it's the smooth initial conditions, and this is what Roger Penrose writes about. What he says is it's very smooth in initial conditions or low entropy at the very beginning of the universe. It's what gives the arrow of time underlying the growth of structure in the universe. In other words, if the structure was already there, it would be there and it would just stay there. The reason it grows is because it wasn't there to begin with, to put it in very simple terms. And what this relates to is that we don't have a proper theory of gravitational entropy in the general case. For black holes we do, you're hearing about that, and we have a very detailed theory of gravitational entropy in the case of black holes. But for a general inhomogeneous system, we simply don't even know if there is entropy. Freeman Dyson says there is no such thing as gravitational entropy. Roger Penrose says there is gravitational entropy, and it's related to the Weyl tensor. I personally believe the latter story, and in fact, I believe that the gravitational entropy is related to the divergence of the electric part of the Weyl tensor, which I could discuss with anybody who wants to go into that kind of detail about general relativity. So Penrose suggests the arrow of time comes from initially zero Weyl tensor. This is Penrose's hypothesis, which then evolves to a highly disordered Weyl tensor as time goes on. And Penrose uses this as an argument for saying the inflationary universe idea does not explain what it is supposed to explain. You will find that set out in The Emperor's New Mind. And there's a book you can look forward to. Roger Penrose has written a new book which summarizes his view of the state of modern physics. It's going to come out in May next year, and it's going to be a fantastic read. Okay. What I just want to say now is that if you now relate this to the real universe, actually the arrow of time problem is different at different epochs. If you take the hot Big Bang era here, where you have equilibrium of matter and radiation and it's very homogeneous, you then get decoupling and structure formation when structure forms. Matter and radiation are decoupled and you're getting stars and galaxies formed, and you then have the epoch where you have got stabilized structures. For instance, the solar system has been stable for billions of years. At this stage, the universe is exceedingly inhomogeneous on a microscale. It may be homogeneous on a macro scale, but on a microscale it is exceedingly inhomogeneous. So it grows from very homogeneous on a microscale to very inhomogeneous on a microscale. At the macro scale, it is supposed to still be homogeneous.